Here are some quick notes on compact object nucleosynthesis to accompany Chapter 7 of To Build a Star. So the purpose of this quick notes here is just to round out our discussion of nucleosynthesis. And so after this, we've covered pretty much most of the bases of how elements are formed in the universe, except for maybe the Big Bang and some specialty processes like spallation and whatnot. But most of the major processes we've covered once we're done with this quick notes. So stars can end their lives in many different ways, as are covered in Chapter 7. And these are often called dead stars, right? Or because it's stellar death that leads to a remnant like a white dwarf or a black hole or a neutron star. But these are really prolific nucleosynthesis environments. There were a ton of the elements in the universe were made. And so you can follow these neat paths here on this diagram and see, depending on how your star started out, roughly how is it going to end its life. And we'll cover different ways that you can make nuclei in these processes, but black holes you might think of as being completely just vacuums, nothing comes out of there. You can actually make elements in a black hole accretion disk. Neutron stars, if they're in a binary pair, these can merge, and you can make very neutron-rich elements in a neutron star merger. You may be tempted to think of an accreting neutron star, an X-ray burst, as a nucleosynthesis environment, but as we discussed, I believe, briefly in the hydrogen burning quick notes, the surface gravity is so large that X-ray bursts are very unlikely contributors, or maybe they contribute a very minor amount to galactical chemical evolution. When you create a white dwarf, if it's in a binary companion, there are a few different ways you can make elements. So you could accrete gas onto the surface potentially and have a type 1a supernova in that way once you drive the mass over the Chandrasekhar mass. You could have two white dwarfs that merge. That would also make a type 1a supernova. We talked about these last time in the supernova nucleosynthesis, so I won't cover them here. But what can also happen is if you're just accreting matter onto the surface of the white dwarf, but you're not driving it over the Chandrasekhar mass, you can have novae that I'll talk about in a bit, and you can make nuclei up to calcium-40 that way. So lots of different ways you can make elements from these so-called dead stars. So in nova nucleosynthesis, what you have is some ordinary star on the main sequence, so maybe our sun or something like that, in a very close orbital separation to a white dwarf. So we're talking like Earth-Sun distances, or even a fraction of Earth-Sun distances, very close together. And your main sequence star, or whatever, your regular star, will have overfilled its Roche lobe, and it will then start transferring gas into this accretion disk onto the surface of your white dwarf. That gas will then build up, and it'll become hot and dense, and eventually you have a bomb. The thing will, the surface layer will burn, and you get basically a lot of light produced for quite a while, and that can make elements up to calcium-40 and potentially beyond there. So this is nova nucleosynthesis, and we talked about the nuclear reactions in the hydrogen burning quick notes briefly. Novae are pretty interesting in that there's a whole host of potential observables from these that can allow us to constrain these environments. So for instance, we can get atomic spectra from the ejecta from the novae. So when an explosion happens on the nova surface, you'll have a cloud of gas that's actually ejected from these, and you can look at the spectra and get spectral lines to see what was made in the nova. There are cosmic dust particles that are found in meteorites that we call pre-solar grains. These are basically dust grains from before the solar system, as is implied by the name, and you get them from meteorites. And so, for instance, there's a famous one called Murchison that is where a lot of the pre-solar grains have been found. And what you can use these pre-solar grains for is to constrain nucleosynthesis environments such as novae. So what you're looking at here is the ratio of two isotopic abundances versus the ratio of two other ones, so nitrogen 14 to 15 versus carbon 12 to carbon 13. pretty much everything on Earth would be located at a given isotopic abundance ratio. When you measure these pre-solar grains that you find tucked away in meteorites, you get very different abundance patterns, and you can do this for lots of different isotopes. And for some of these, you have a characteristic signature of a nova. And we believe that then those are material made in a nova, and so we compare those to model calculations to try to constrain what happened in those environments. And then maybe in the future you could potentially observe gamma rays from the short-lived nuclei that are created in this environment. So the nova nucleosynthesis makes very proton-rich nuclei up to calcium-40. Some of these are going to be short-lived and produce gamma rays. At the moment, no one has detected them yet, but it in principle could be possible. And then another possibility that has not been detected yet is you could potentially use molecular rotations. So from molecular rotations, you can actually you can tell the difference between, for instance, this aluminum fluoride, whether you have aluminum 26 or 27, and those lines could potentially be used to get abundances from nova nucleosynthesis. But again, this is a possibility. This has not been done yet. Now, from moving on to neutron stars, as I mentioned, the accreting neutron stars are not really of interest here for nucleosynthesis, but neutron star mergers, of course, are. So here you have two stars that eventually evolved to be neutron stars. They're in a very close orbital separation, and the environment gets super hot and super dense and starts out with a lot of extra neutrons, and so of course you can get neutron-rich nucleosynthesis going on here. A variety of things can happen. You have these tidal tails that will have characteristic temperature and density trajectories. You have the region ejected here from this collision region, if you want to call it that. You have nucleosynthesis going on near the poles, where you have, for instance, neutrino-driven winds driving material out. So lots of different nucleosynthesis can happen in these environments. And we know a lot about these neutron star mergers now because one's actually been observed. So what you can look at here is the frequency in the vertical axis versus the time before the neutron star merger. And if you look carefully here, you see a green line growing in intensity. It's getting darker and darker. And so this frequency is being picked up. These neutron stars are spiraling inward. They're spiraling at a faster and faster frequency as they get closer together. And then you really start to run away as you get close to the merger regime. And if you would like the audio to go along with that, you can follow this YouTube link here. We can get even more information from the neutron star merger if we look near the end of the merger when it happened. This is actually data from black holes merging, but you get something similar for neutron stars. So you have the frequency in the vertical axis, time in the horizontal, and this is leading up to the merger. And you can get these interesting patterns here, and these can be interpreted to tell you something about the neutron stars themselves. So for instance, the relative masses that they have. And in terms of nucleosynthesis, the signature that we get is this beautiful thing called a kilonova that had been predicted previously but was finally observed with the first neutron star merger that we got gravitational waves with, which was kind of lucky. So the kilonova is about 1,000 times brighter than a nova. That's why it's called kilonova. There are other names for it too. I think macronova is an old one in the literature. But in any case, you can see these across the electromagnetic spectrum. So in the optical, for instance, you see this region get bright and then dim over the course of a few days here. And you can also see more information from the kilonova if you separate it by the spectrum, so by the color. So it starts out bright and blue, and then as it decays, the spectrum actually turns more and more red. And the thinking is that you have low opacity, iron peak, and light R process elements here that are dominating your spectra. And then later on, you have radioactive decay and high opacity, heavy R process elements. So the lanthanides, for instance, signature of that there. And the observations agree remarkably well with the theory, which is pretty cool. So we now know that neutron star mergers are a site of our process elements. It's not really a question. Question is whether or not it's the site, what variety of nucleosynthesis conditions do we have, that is still unknown. And then finally, we can get nucleosynthesis from black holes, as I mentioned at the beginning. So you might think, wait a second, like, nothing escapes a black hole, right? So how is nucleosynthesis occurring? Keep in mind that that's only nothing escapes the Schwarzschild radius, right? If you're outside of that, you can still escape it. So as long as your material doesn't get too close, then of course you can have something happen near that black hole, escape, and then, for instance, enrich the universe in those abundances. So one possible site is, instead of two neutron stars merging, you could have a neutron star and a black hole merge. And basically what happens is the neutron star gets ripped apart by the black hole. You create then an accretion disk around this massive remnant, which of course will be a black hole. But the ripped apart neutron star guts are then around this neutron star, or not neutron star, sorry, this black hole remnant, and they're going to accrete onto it, and that's going to create a very hot environment. And just because of the hydrodynamics, and also neutrinos being driven off this hot environment, you can get material ejected from here. So you have very hot material, and that can be ejected. And it's hot enough that that can drive nucleosynthesis. So we're talking a few to like 10 Schwarzschild radii away from our neutron star. This material is undergoing nucleosynthesis, and it could, for instance, in principle, contribute to the cosmic R process abundances. So here you have the abundance on the vertical axis versus the mass number, and then the observed solar R process pattern. These are the symbols, and these are two different model calculations, assuming different conditions around your black hole accretion disk. And you see you can maybe make some R process elements here. So kind of neat that even black holes can get in on the nucleosynthesis production. So that's it. We've covered most of the bases then for nucleosynthesis this semester. And that is it for these quick notes on compact object nucleosynthesis. And that is it for the quick notes for this semester of Astronomy 4201.